Good evening, everyone, and welcome back to our series of presentations from the Kavli Institute for Particle Astrophysics and Cosmology at Stanford University. We hope that wherever you're joining us from tonight, that you're safe and healthy, and our thoughts go out to all of those who've been affected by the tragic wildfires in California. But this evening, we invite you to join us to discover our universe. My name's Dan Wilkins, and I'm an astrophysics research scientist at kipac, and I'm the coordinator of our public talk series. You can find out all about the varied events we've got coming up for you online over on our website, kipac.stanford.edu/discover. You can find out all about the talks we've got coming up, and you can watch any of our past talks again. But tonight, it's my great pleasure to introduce Dr. Fang. Ke obtained her doctorate in astrophysics from the University of Chicago in 2015. And in 2018, she was awarded NASA's prestigious Einstein Fellowship, which brought her to Stanford to pursue her program of research. Now, Ke is an expert in piecing together the information that we receive from the universe from a multitude of different messengers. These include high-energy gamma-ray radiation, ultralight particles that we know as neutrinos, and cosmic rays, and she uses these to study the extreme activities of our universe. And tonight we're delighted to have Ke here to tell us all about some of her studies using these energetic bullets from outer space. Now we invite you to submit your questions to Ke. We'll be having a Q&A with Dr. Fang after the talk. So if you're joining us on Zoom, head down to the bottom of your screen and press the Q&A button. You can send in your questions to us there. Or if you're joining us over on YouTube, you can send in your questions using the chat feature. But for now, I'll hand over to Dr. Ke Fang.
Thank you, Dan. Let me share my screen. Does that look good?
Yeah, looks great.
Okay, great. So it is a great pleasure to be here and talk about the energetic bullets sent from the outer space. So in the nights, when we step out, look at the sky, you see this beautiful stars, Milky Way in the sky. The reason you see them is because these objects are shining in a wavelength that human eyes are sensitive to. But in addition to those optical lights, they actually also emit cosmic rays. So cosmic rays are outer space messengers, and they are everywhere. So for example, we open up our hand in the air, and in this very moment, we see there are many particles going through our hand. We just don't see them because they are not emitting in the lights that we can see. So this imaginary picture showing on this slide is an imaginary sketch of a distant source that's emitting those cosmic rays. In using detectors that we can see those cosmic rays exactly like what is showing here. So cosmic rays were discovered only in the last century. Back in 1910s, people realized there are ionization in the Earth's atmosphere. And people initially thought that those radiation are coming from the Earth's surface, although there were pioneers thinking that those radiation are coming from outer space. So to address the debate, to understand the origin of those cosmic rays, those radiation, Victor Haas, who is this brave man sitting inside a balloon, launched his own experiment by flying himself up to a distance 5 kilometers above the ground. And through this experiment, he measured the radiation level at 5 kilometer height is almost twice that at the sea level. So that suggests that this radiation is indeed going higher when you're going higher in the atmosphere. So that suggests the name of the nature of those rays as radiation from outer space. And that's also where the name of the cosmic rays comes from, cosmic ray referring to outer space and not coming from the local Earth. This discovery was awarded the Nobel Prize in Physics in 1936. So just to give you a sense about how the cosmic ray looks like, and also how our brave man Victor Haas did his experiment, this picture here showing you how an energetic bullet, when they enter into the Earth's atmosphere, they will develop a shower-like structure. So how it looks like is you can see at the top of this figure, there is an array, and the array started to interact with the atoms in the Earth's atmosphere. That interaction is injecting several children particle, and those children particle is less energetic, but still can generate their children and grandchildren. That's why we see this kind of a shower structure. That's why we call them air shower, like the shower you take every day. So the passenger jet you see in the middle of this plot is what we usually take at a height about 10,000 meters or 30,000 feet. And Victor Haas was almost half that height to make the discovery of cosmic rays. That shows how men have been brave enough to pursue the science. Okay, so that was the first question, first mystery solved. It's cosmic, it's coming from outer space. And from the name, you might already wonder, the rays are people what usually refer as lights and photons. And indeed, scientists were wondering about the nature of those cosmic rays. Are they really photons, like the lights we see, or are they actual particles? So this question got an answer in the 1930s when people realized difference in the intensities of cosmic rays arriving from the east and the west. We know our Earth has a geomagnetic field, and it has a certain direction. It's coming from the south to the north. So given this fixed structure of Earth's magnetosphere, charged particles would be their direction would be interrupted when they get into the Earth's atmosphere. And the fact that there is a difference in the cosmic ray intensities when they're coming from the east and coming from the west suggests that these particles must be charged. So they are not lights like what we see from the stars. They are actual charged particles like protons or helium nuclei. So these cosmic rays are quite fascinating, not because they are different from the lights, but also because they are some of the most energetic particles in the universe. Their energy can be as high as 10 to the 20 electron volts. So electron volts is what we use to, as a unit in the physics, is what we use to measure the energy. So the ultra high energy cosmic rays, when they were discovered because of their extreme energy, people were initially called them, oh my God, particles. So just to give you a sense how high that number is, the man-made accelerator on the Earth on the right-hand side of this plot is able to reach an energy range of 10 to the 14 electron volts, which is 1,000,000 times lower than the ones we see from the nature. And yet this is the largest accelerator on the Earth. It covers almost the size of a town. And even if we expand the size of the Large Hadron Collider and use the entire Earth as a particle accelerator, we would still not be able to reach the number that we see from the nature. If that still does not impress you, the kinetic energy of a spitting baseball is at the range of 10 to the 20 electron volts. So you play the baseball, you know how fast they are and how painful if they hit you. But still, a baseball is containing lots and lots of atoms for at least 10 to the 23 number of them. So if you're thinking to compressing the 10 to the 23 number of atoms in your baseball in just one, and that is the particle you get from the universe. So the discovery of these oh my God particles was done in 1960 by John Lindsley in New Mexico. This is a picture of him just using one of his detectors to measure those air showers generated by one of those particles. So you probably are wondering what is that pile of thing looks like, something covered by the grass. So that is a cosmic ray detector. A cosmic ray detector is functioning like this. So you have a sealed box that is a tank containing liquid. And when cosmic rays enter, because these carry extreme energy, these particles fly almost with a speed almost close to the speed of the light. So they are relativistic, and they would generate relativistic effects when it penetrating the liquid. So the Florence lights and the Cherenkov light generated when this particle going through the liquid can be collected by a device called photomultiplier. They are like multiplying the number of the photons received when the reaction happened. So by collecting those photons, we know the energy and the direction of the cosmic rays. So that's how scientists measure those cosmic rays. This is a unit called ground-based liquid scintillator. This is the same unit used back in 1960s with improvements. Now it is expanding to a large area. So what's showing here is one such detector called Pierre Auger Observatory. Pierre Auger Observatory is a collection of those units that I show on the previous page. And there are 3,000 of them, cover a whole total area of 3,000 kilometers square. So each gray point on this figure corresponding to one such tanks. In addition, it contains 4 Florence telescopes to look at the Florence lights generated when those energetic particles going through the Earth's atmosphere. The Pierre Auger Observatory is in Argentina, and on the right-hand side, this is a figure showing a unit of the water tank in actual size. In the Northern Hemisphere, we also have a similar detector called telescope array. Telescope array has a setup very similar to Pierre Auger. It has 700 kilometer square water Cherenkov detector array plus 3 Florence telescopes. Right now, telescope array is being expanded to 4 times at its initial site in Utah, and it's going to be matching the one from the Southern Hemisphere. Here is some simulation showing you what scientists see from those detectors. So those shining little backgrounds, little dots are the background noise coming from the cosmic rays from the Earth's atmosphere. When there is a real outer space passenger comes in, it shows up as this bright dot that crossing our windows from once in a while. So by tracing those bright signals and get them out of the background, we can measure those cosmic rays at extreme energy. So both Pierre Auger Observatory and Telescope Array have been running for a while. Pierre Auger is reaching its 20-year mark, and this is what we have learned with 20 years of dedicated observation. This is a so-called spectrum. So spectrum in astronomy means essentially the distribution, the number distribution of the energy of the photons or the energy of the particles. The y-axis is a scaled number density distribution for particles in each energy band in the x-axis, and these energy bands are in logarithmic scale. And the numbers on this plot are corresponding to the number of actual events we see in each energy band. So you can see that after 20 years of accumulation, we do see quite a lot of those extreme energy particles, including some of those oh my god ones. But you probably immediately would notice some interesting facts about this spectrum. That is, these oh my god particles are really rare. There seems to be something happening to them that somehow the distribution cuts off when they hit this energy above 10 to the 19.5 electron volts-ish, and then they seems to be no longer coming in. And there are very little amount of them. So this effect was already predicted back in 1960s when the cosmic microwave background was initially discovered. So we know that we are not living in a vacuum. We have cosmic microwave background everywhere coming from the initial Big Bang. And those photons are quite abundant and uniform. So when ultra high energy cosmic rays traveling for a long distance, they could meet up one of those background photons and interact. That interaction is going to take away the energy of the primary particle, turn them into secondary particles like charged pions and neutral pions. And and make an absorb. So they absorb those primary particles. This interaction would happen for a distance about 100 megaparsec. So whenever cosmic rays travel for a distance larger than that, they will have a good chance to be eaten by a CMB photon. So what is 100 megaparsec? It probably doesn't really give a sense to you. Well, 100 megaparsec correspond to 321 million light years. Okay, I know that still doesn't resonate. Let's look at this diagram. It's not to scale, but it shows roughly where we are. So here is our Earth on the front. We are sitting in a solar system. It's not to scale, but you can see our favorite neighbor, Jupiter, Saturn are there. Our solar system are sitting on the disk of a Milky Way galaxy, galaxy at a distance about halfway to the center of the Milky Way. We're on the disk, and Milky Way is a pretty ancient big disk galaxy. And our Milky Galaxy is, in addition, belonging to one of those local groups, which include a few other large galaxies like Milky Way, plus many, many small mini galaxies. And this local group, in addition, is a component of this large supercluster. So by this time, we are already a tiny, tiny little dot in the figure. And yet, the local supercluster is just one small bright dot on the left-hand side, on this picture, showing on the left-hand side, which shows the large-scale structure of the universe. This cosmic web is the actual big structures developed from the beginning of the universe. And we're just sitting in one of those webs, and 100 megaparsec is corresponding to roughly the distance contained in this silver look, this gray and silver look box. So we know roughly, because of the attenuation of the cosmic rays that we see when we measure those number of the oh my god particles, they cannot really travel beyond this distance listed in this silver box. On the other hand, in other words, everything we see, those oh my god particles, are really sitting inside, are coming from sources inside this silver box. Great that we know roughly where they come from. It's also good that with the cosmic ray detectors, we have some sense about the chemical composition of those particles. So the way we observe the chemical composition of those particles is through the air shower development. So remember the air shower I showed you on the beginning of the talk. The cosmic ray comes in, develop a big shower, and this development depends on the nature of those particles. Here is a movie showing you how Here is a movie showing you how these air showers develop when they enter the Earth's atmosphere. This is shown in 3D projection. So the one on the top left is the one you look from the bottom of the air shower. So you can see that the air shower develops to some maximum shape when they enter the Earth's atmosphere for tens of kilometers. And then this shape gets thinner. So the distance up to which the air shower develops to its maximum shape is sensitive to the nature of those particles. It's different from protons to ion nuclei. It's different for muons or electrons. So that is how we detect the chemical composition. So on the right-hand side is the result for the chemical composition of those cosmic rays, again, based on 20 years of observation. So the red and the blue curve corresponding to the air shower depths had the composition of the particle being pure proton or pure ion. And the data points in the middle is corresponding to the actual measurement. So you can see that the nature is not boring. It's sending a changing chemical composition of those nuclei. You can see that around 10 to the 18.5 electron volts, the composition is mostly consistent with being proton. But when you go up to higher energy, when you enter this oh my god regime, they are getting into an intermediate or even heavy composition like iron particles. So there are quite a lot of going on out there in that energy range when you go into the highest range of those cosmic rays. And the third measurable we can do with those particles is the arrival directions. So there's also an unexpected feature. As shown in this figure, the red color indicating the region where we see an excess of the arrival direction of those ultra high energy cosmic rays, whereas the blue region corresponding to a deficit in the arrival number of those particles. So you can see there is a preferred direction in the sky where those particles comes from. So the reason of this dipole and it's still unknown, and it could be caused by either the change of the particle direction when they enter the galactic magnetic field, or it can be caused by some nearby sources that's particular in some favored direction that producing this dipolar structure. This is still an active region of research right now. Great, so I hope that gives you some basic introduction about those energetic bullets. And here is a cartoon showing you how the world, the universe of those cosmic rays looks like. We are on the Earth, and we have this Earth's atmosphere, which generating all of those air showers. And yet when we go out to look at in the universe, somewhere there is some kind of active sources that is shining and emitting those bullets. And those bullets will enter the galactic and extragalactic space and producing secondary particles as if they are doing in the Earth's atmosphere, and then generating secondary particles like neutrinos and photons. And yet the cosmic rays itself may travel after years and years of delay in the magnetic field and finally arrive the Earth. So in the next few the next time of my talk is going to divide it by focusing different component of this cartoon, starting by focusing on the sources. So given all of those wonder of these crazy particles we see from the nature, you might be already thinking who are actually emitting those particles. Well, we do not yet have an answer, but we have some good candidates out there. The first candidate is the jets made by black holes, either supermassive or stellar mass black holes. We know that these active accretions of supermassive or stellar mass black holes is going to generate very powerful outflows, relativistic outflows like jets as shown in this little movie here. And those jets carry extraordinary amount of energy and magnetic field that will provide a site that is favorable for accelerated particle to such extreme energies. A second type of possible sources are the intergalactic medium accretion shocks. We have large-scale structures, and we are, as I showed you earlier, we are sitting in one of those little dots, and the structures connecting those dots can be really large, and sometimes they form shocks in between those galaxy clusters. And those shocks have extreme sizes. Although their magnetic field are not that strong, they can still make particles to that extreme energy. And a third type of sources is also amazing sources. They are neutron stars. So these are very tiny stars. They have a size almost comparable to the Bay Area, only 10 kilometer-ish to the stellar surface, and the nebula that's much bigger than that. And this image here is showing you the Crab pulsar, which was born only 1,000 years ago, and at a distance of about 60,500 light years, so very close to us. These different colors are what we see in different waveband. In the highest band in X-rays, shown in the purple here, you can see that this very crazy, violent source, the heart of the pulsar. You can see this torus and the jet structure. That's the star, the neutron star inside. And in lower energy, in the UV band, for example, you can see this big nebula, which has a crab shape, but that's why it's called crab nebula. And that nebula is a plasma powered by the central source. So this whole system provides many good locations for extreme particle acceleration. So they are also very possible sources for those energetic bullets. So we do have many good candidates, but we still do not know yet, after all these years of observation and theoretical study, because it's a really hard question to ask where these cosmic rays come from. The fundamental difficulty comes from the fact that the cosmic rays are charged particles, so they don't travel in a straight direction. So here is a cartoon showing you that we have a source out there, and here is our Milky Way, and we have a dark matter halo surrounding us with a potential moderate magnetic field. So the photons will come in a straight line because they don't have charges. But for cosmic rays, for ultra high energy cosmic rays above 10 to the 19 electron volts, they will have a magnetic field. They will already be deflected by the magnetic field. So by the time they arrive on the Earth, and when we trace back to their coming direction, we might find out some direction that's degrees or tens of degrees away from their initial direction. And what's worse, for cosmic rays at an energy lower than about 10 to the 18 electron volts, they will suffer strongly in the galactic magnetic field. So by the time they get to the Earth, they have already completely lost their information their directional information. So it's very difficult for us to trace back to understand where they come from. And that is why, to solve this ancient century-old question, we do need to find the ashes of the smoking gun. So what is the ashes of the smoking gun? Going back to our cartoon here, I showed you that we have some sources coming out, and the cosmic rays, while they travel on the Earth, to the Earth, they could interact and produce secondary particles like photons and neutrinos. These secondary particles, their children, are neutral particles, so they are no longer interrupted. Their direction are no longer interrupted by the magnetic field, and they can trace back to the original direction of their parents. So I would first focus on the neutrino. Here are a introduction to the existing high energy neutrino observatories on the Earth. We have IceCube. IceCube is a kilometer-size array in a South Pole in Antarctica at the geographic South Pole. So this is our geographic South Pole, and you can see that right now we have 86 streams of photomultipliers going down on the ice of Antarctica. It's an outstanding experiment, has a very large size just compared to the Eiffel Tower, if that makes sense to you. If the size makes sense to you, this is the actual detector. It took 6 years for scientists to finish constructing this lab, and right now it has been operating since 2011 in a full configuration. Also in Antarctica, there is a balloon-borne experiment called ANITA. The balloon is flying in the atmosphere on top of Antarctica, trying to catch in those particles as well. And down in the Mediterranean, we have streams of photomultiplier trying to detecting the particle with a similar detection mechanism as IceCube, except that it's inside the water. It's called Antares. So the way IceCube detect high-energy neutrino is like this. The neutrino would come in and hit the ice, producing a muon or a secondary particle. In this example of the muon is produced, it may travel through the, it may travel through the strings of photomultiplier, and the light is going to be collected by the detector and transmitted back to the center, to the lab on the ground. So the location of so you can see that by having this muon travels through the detector, we can record the number of the photons produced deposited by this charged particle, and we know the original direction where it comes from. So this is how the detector works. And the first neutrino detection was achieved in November 2013, and there were two PeV 10 to the 15 electron volt neutrino being observed. And back then, because these are only two of them, they even have names, Ernie and Bert. And on the right-hand side, 7 years later, here is a sky map of the neutrinos IceCube has collected. Now we have a lot more of them, and they don't have names anymore. But the good news is we have a better sense about how they look like in the sky. The different colors here are indicating corresponding to different ways that those neutrinos are identified in the detector. You can see that they are not, this is the dashed line is the galactic point. So you can see that they are not mostly galactic. Most of them are coming from extragalactic universe, very much more distant than our own Milky Way. And the distribution of those observed events seem to be almost diffusive and isotropic in the sky. There's no preferred direction. So the origin of the bulk of those neutrinos are still unknown, although there are some first hints about some correlation of individual events with astronomical events. Okay, so that's neutrinos. And photons. Photons are also very nice particles, and at those extreme energies, they are called gamma rays. So high energy and very high energy gamma rays are constantly monitored on the Earth. So at GeV ranges 10 to the 9 electron volts, Fermi Lab, the Large Area Telescope on board Fermi satellite, which is co-hosted at SLAC, is monitoring the sky in the full sky, monitoring the full sky. And then at above TeV, above 10 to the 12 electron volts, there are two techniques to detect those very high energy gamma rays. We can use imaging atmospheric Cherenkov telescopes. There are three major experiments there called HASS, MAGIC, and VERITAS, like those imaging telescopes looking for the Cherenkov lights generated by those gamma rays. A second way to detecting those very high energy gamma rays is using high altitude water Cherenkov observatories. So these are the water tanks, very similar to the ones you see earlier, observing those cosmic rays, but configured to maximize to see the gamma rays. So this is using the air shower generated by those very high energy photons to track their original direction. So here is how the GeV sky looks like. This is detected by Fermi Lab, and you can see that our night sky in a waveband that human eyes cannot access looks like this. This very bright point is our Milky Way, our own Milky Way. There are a lot of very bright sources along the disk. Essentially, the whole disk is being brightened, is being illuminated. And there are many bright sources like the supernova remnant on them. And also, I should mention that in the extragalactic plane, there are also many distant sources. Okay, so when removing the bright foreground of the galaxy, we see a set of bright bubbles on top of the galactic center. These bubbles have a height almost about 8 kiloparsec, and they are symmetric below and above the galactic plane. And they are believed to be bubbles inflated by the previous activities by the supermassive black holes at the center of our own Milky Way. These are extraordinary footprint of the previous histories of our own Milky Way black hole. This is how the sky looks like at even higher energy, 1,000 times than the one we see earlier. So the TeV sky has much less sources, partially because the distant sources are absorbed when they travel to the Earth. So in the TeV sky of the Hawk observatory, we see only two nearby extragalactic sources, the two Macarians. They are jets from the black hole shining toward our direction. The plane is indicated by this white dashed line. So this is our galactic plane. We see lots of interesting sources there as well. These two are the pulsars, and the crab is what I introduced you earlier, the crab-like nebula and the pulsar. And then at the highest energy sky map, so these are the sources significant to Hawk above an energy of 100 TeV, so 10 to the 14 electron volts now. All of the three sources seems to be associated with pulsars, so the neutron stars. Yet it's still unknown and a mystery how such TeV sources, how they are so extended. These are pretty large, much larger than the actual size of the star. So it seems like those neutron stars, although themselves are quite small, they are impacting a very big surrounding region of them. So some interesting sources next door, looks like this. So this is a mini active black hole sitting at a distance of 5.5 kiloparsec inside the galaxy. The location is there in the TeV sky map. So this is a microquasar, or what we call as a mini quasar inside the galaxy. So this is how it looks like in the in the radio band, this bluish color, and in the X-ray band, the reddish color image on the right bottom, as well as in the eyes of Hawk at an energy above 20 TeV, 2 times 10 to the 13 electron volts. So we now know this is these black dots in the middle is the location where the black hole sits. The black hole itself has a mass about 10 times the size of our sun, the mass of our sun. So it's not that massive. However, even it's not that big, it already powers a set of very powerful jets as seen in both ends of it. It's symmetric. And when the black hole was born, it generated a supernova remnant, looks like this surrounding this fish shape image on the top of this plot. And this fat head and the tail of the fish is believed to be generated by the jets penetrating a circle-like supernova remnant. So we detected very high energy gamma ray in the jet of this set of the black hole, showing for the first time an evidence that extreme energy particles can be accelerated in such distance of the black hole jets. So even though this is a mini black hole, they are already extremely powerful. Another interesting source inside our galaxy is a star formation region. So this is so-called Cygnus cocoon. So this is a cocoon-like structure. It's very big. It has a size radius almost about 3 degrees, and it's a cocoon in the Cygnus constellation. On the left-hand side is how it looks like in the infrared map. You can see that it consists of quite a lot of bright stars. They are O-type and B-type stars, very active and young stars that are very they are still forming. So these are newly born stars. And on the right side, you see the image observed by both Fermi and Hawk observatories of this cocoon. So apparently, this newly formed cocoon inflated by the starburst activities is also energetic in producing those energetic bullets, and it's extended. These observation of those cocoons suggests that these are regions producing very freshly accelerated cosmic rays. So it's quite exciting to see something is actually happening next door. Okay, so we already made lots of progress all the way from our pioneers in the beginning of the last century, and we have made the first detection of neutrinos. We understand quite a lot about the exciting sources next door. And the step to go toward the future is we want to make our sensitivity of the detectors even better. So we will be able to see more such events to identify their origin and to solve eventually the mystery of the origin of those omega particles. The neutrino detectors right now is sitting like that area, and a plan is trying to expand IceCube Observatory by 10 times bigger in volume. So this is the current IceCube, and we hope to build up them to be at least 10 times bigger so that the sensitivity would be good enough to collect neutrinos from some point sources. So we can actually not only see the event itself, but also see the source behind those neutrinos. There are also other plans in detecting the ultra-high energy neutrinos. For example, POEMA project is aiming to using 2 synchronized satellites to look downwards on the Earth's atmosphere to look for those air showers coming from primary particles, including neutrinos. And GRAND, the giant radio array for neutrino detection, is another proposal trying to using radio arrays sitting on the mountains to see the showers generated by tau neutrinos when they penetrating the Earth or the mountains. And gamma rays, we also have plans to build bigger gamma ray detectors. So the current wide field of view gamma ray detectors like HAWK are mostly on the northern hemisphere. So we cannot really see this galactic center. We cannot see the Fermi bubbles in an even higher energy ranges. So that's why there is a plan to build up a 1,000 wide field gamma ray observatories to access the sky regions that are currently not accessible. There is also a plan of an upgrade of the current generation imaging atmospheric Cherenkov telescopes to this Cherenkov telescope array. There is also a LASSO experiment being built to observe the northern sky with better sensitivity. These are all for very high energy gamma rays, so gamma rays above 10 to the 10 to the 11 to 10 to the 12 electron volts. And in the medium energy, which is a energy range that traditionally not so accessible to astronomers, the all-sky medium energy gamma ray observatory AMIGO, proposed by the same team at NASA, is trying to explore this energy range in the around 10 to the 6 electron volts MEeV range detectors. So I will end my talk by showing you this interesting cartoon and to share you the excitement of scientists in this field. We are living in a multi-messenger era. We are no longer only see our universe through the lights that human eyes or detectors are sensitive to. In addition to lights, we see the universe through neutrinos, cosmic rays, gravitational waves. Supposedly there are a merger of massive black holes or neutron stars, and that can generate gravitational waves. And the process can generating shocks or magnetic field structures that produce extreme energy bullets. And those bullets, when they shooting through the intercluster medium or interstellar medium, producing secondary neutrinos and gamma rays like we described earlier. And by measuring the gravitational waves, the gamma rays, the neutrinos, the cosmic rays, when they eventually arrive on the Earth, we would be able to put up the pieces together to see a complete initial image of the universe. So by collecting the messages sent out by the universe, we can have a better picture of what's happening out there, millions and millions light years away from here. Thank you so much.
Wow, thank you, Kerr. It really is amazing to think of these high energy cosmic rays. You talked about these ones with energy equivalent to a baseball. Now, if we think about a typical baseball, about 5 ounces traveling at 100 miles an hour, if it's a good hitter, all of that energy, but that baseball contains a billion atoms, and
Right.
We're talking about just a single subatomic particle with that same energy in it. It really is amazing to think of that.
Exactly.
So if one of these cosmic baseballs were to hit us, I mean, with all that energy they have, would we feel it? What would it do to us?
Right. So the good news is, although they are energetic, they are like bullets. The good news is they are really, really tiny. So, and they are really, really rare. The reason we are using such big detectors and waiting for 20 years to observe them is indeed because the rate of those particles is really rare. So the rate of those particles is roughly 1 per kilometer square per century. So thinking about the size of our body, the chance of getting one such particle is extremely low. So we don't think that can actually produce damage to the human body. And also because our Earth's atmosphere serve as a shell to those particles. So it's not likely that they will hit you before they developed into many, many smaller pieces. So that's how it looks like.
So we're thankful for many reasons on Earth to have that atmosphere around us that's going to take all the energy out of that cosmic ray and separate it into that whole shower of
exactly
showed.
Right.
So some of these were subatomic particles, but you also talked about them being made of iron. Does that mean it's a whole iron atom flying to us through space?
Right. So at that extreme energy, they are relativistic particles. So it's more like a bag of the elementary particles when they hit on another particle. But yes, so by the time we observe them on the Earth, we see that it's either a bag of 56 little proton-like elementary particles, clustering of elementary particles, or one of them, they can make a difference in the distribution of their air shower.
Sure. And so you talked about how we detect these cosmic rays, and how we have these detectors, these big tanks of liquid on the ground, that when the cosmic ray hits it, it produces light that we can see. We had a question come in as to exactly how does that high energy cosmic ray, how does that particle turn into light?
Oh, sure. So the process is an interesting question. So it's a relativistic effect. These particles at relativistic energy, they travel at a speed like 99.9999% of the speed of the light in a vacuum. And then in a liquid with a index, which is essentially higher than 1, then these particles will have an effect and producing chunk of light. So their phase speed would exceeding the speed of the light, and that would cause a local effect producing those chunk of light. So it's a radiation. So those chunk of light is the one that we use to track those relativistic particles.
And I guess because you say that the particles traveling faster than that local speed of
right.
the wave it's producing, you can almost think of it like a sonic boom of light. So you get that light flash.
Yes, in that medium. Yeah.
So talking of cosmic ray detectors, we've actually just had a comment from an astronomer on the line who says that they're familiar with cosmic rays as these annoying streaks they get on their images in their CCD camera on the telescope. So I guess we're not seeing those ultra high energy cosmic rays hitting the chip. It would be the shower, I guess, that's produced in the atmosphere. Is that right?
Right. Because they are so energetic. So there is no chance they can escape the Earth's atmosphere to hit the detector directly. They will most likely already colliding many times by the time they reach the ground.
Yeah, so we're seeing them after they've lost their energy through all those collisions.
Right, we're seeing a big shower. We're being like showered by those primary cosmic rays.
Yeah. So you talked about black holes as being a source of these cosmic rays. Now, when we hear about black holes, we often think of them as being these extreme collapsed objects whose gravity is so strong that nothing, not even light, can escape from them. So how is it that a black hole, do we think, is able to launch these particles that not only are they escaping the black hole, but they're escaping at these enormous speeds?
Right. So the black hole itself, specifically the event horizon, is the distance, the size very close to the black hole that will absorb everything traveling at the speed of the light. So nothing can escape the hole within that distance. But beyond that distance, it is still possible to get out from the region. And specifically beyond that distance and this accretion disk, this big disk accreting those black holes, those regions, as well as the jets, which are the jets perpendicular to the accretion disk, those are the regions that provide plausible sites for particle acceleration. So in short, the answer is that the accelerator sits far away from the black hole enough to allow the escape of those particles.
Yeah, so it's the energized material, sort of in its final moments, if you like, before it falls into the black hole. It's at such high energy, and it's perhaps got very strong magnetic fields around it, and it's that's producing these accelerators.
Right.
So we don't have to worry that anything's managing to escape the black hole itself.
Yes.
So when these cosmic rays travel to us through the galaxy, they're getting deflected. You showed they're taking this complicated path as they wiggle around the galaxy, but the light and the neutrinos are coming in a straight line towards us. So how confident can we be that we are correctly associating the cosmic rays with the light and with the other things we see coming from these smoking gun sources?
Right. So that's an interesting question. So at lower energy, lower meaning energy below 10 to the 18 electron volts ish, if you remember the cartoon that I showed during the talk, these particles gyrate a lot in the galactic magnetic field. So they really lost their directional information. But for the ultra high energy ones, these oh my god particles, their energy is high enough to allow them only travel away from their original direction a little bit. So you can still see some features or patterns in their arrival direction by looking the full sky distribution. For example, there are some preferred direction that we see already in the sky. And in addition, those energetic particles won't travel too far away from their original direction or original location before they interact and producing a secondary neutral particle like photons and neutrino. So that's why when we see those secondary particles, they serve like a smoking gun to the initial direction, because the shorter distance compared to by which they produce those neutral particles, it's small enough comparing to the distance from the source to the observer. So we are pretty confident that those secondary particles already can be used to point back.
Yeah, so they're still kind of in the same direction. And if we look for these sort of bright events, so these flares or flashes, we look for the coincidence of the different events and them being close together on the sky, and we can put all of that information together.
Yeah.
So early on in your talk, you spoke about how the Earth's magnetic field causes the cosmic rays to change direction, and that was what allowed us to learn that they were particles and not photons and not light.
Right. Yes.
Because the light wouldn't get deflected like that. So does the field just affect the direction the rays are traveling when they come through the Earth's magnetic field, or does it change other aspects of them?
So so for the lower energy cosmic rays, the one you see a lot going through your hand, the Earth's magnetic field is large enough to distort their direction.
Mm.
But for the oh my God particles, the Earth's atmosphere is tiny enough to be almost negligible. Instead, the magnetic field of our Milky Way is more prominent in changing in the size to change the direction of those particles. And magnetic field mostly change the direction of charged particles instead of doing anything else.
And when those particles hit our atmosphere and they separate into that shower of different particles, does that shower depend on the different cosmic sources of the cosmic ray? Do cosmic rays from different origins separate in different ways? How much can we learn from that shower about what hit us?
Right. The shower, by the time they develop the shower, they are mostly depend only on the particle itself.
Okay.
So we can see that the size of the shower or the depths of the shower are mostly determined by the energy and the nature, if it's a proton or it's ion of those cosmic rays. And in the secondary particle case, neutral photons or neutrinos, it could be the case that a lot of them arrive at the same time because they are not delayed by the magnetic field. So those big clump of them comes in at the same time. That can give you some time coincidence signal. So you can know that, okay, these guys are likely coming from some same event very distant away.
Thank you. And I can see actually your talks got some of our audience starting to think about their own experiments. And we actually had a question, because these cosmic rays come in as such high energy into our atmosphere, could we design an experiment to put in space to make a really high energy particle accelerator if we're able to grab these particles that are already so high energy, or would that be very difficult to do?
Right. So the reason that scientists build detectors on the ground is because these particles are really rare. So remember that we have already a coverage of 3,000 kilometers square on the Earth, and that still takes 20 years to collect enough statistics to make statistically significant observations. So if you can be really lucky in a space to do the same observation, but the chance is really low unless you can build up a big detector in a space.
Yeah, you'd be very lucky. You spend all that time and money building the machine, and then
Right. Or if you stay for 100 years and waiting for one particle.
Yeah, well, thank you. We've just got time for one more question before we wrap up. So we can really see this era of multi-messenger astronomy is developing fast. And not long ago, we just thought of astronomy and studying our universe just in terms of the light that we see coming through the sky. And now we've had the addition of these cosmic rays and also gravitational waves, the ripples in space itself. So what breakthrough in astrophysics are you most looking forward to in the next 10 years?
Thanks. So in the past 10 years, there are many excitements. We made the first detection of neutrinos, and also there was the first neutron star merger. So apparently in the history of astronomy, many advances were made by those extraordinary events, like this neutron star merger, GW170817, happened 3 years ago. That event only gave us understanding about the kilonova. We understand the short gamma burst being formed after two neutron star mergers, and we were able to detect emissions and gamma rays from those sources as well. So I would hope that in the next 10 years, we have even better detectors with nice sensitivities, and I would hope to have another such event like the neutron star merger or some nearby transient, some nearby bright star activities or black hole activities that can send multi-messenger signals so that we can see them using different
telescopes, different observatories, and see them in different messengers, so that can give us an understanding, an accurate understanding about the physics of those excellent sources in the universe.
So I guess it's the combination, isn't it, of the universe being kind enough to send us these messages from these really fascinating events, such as that neutron star merger that we saw a couple of years ago, but also us being ready with the machinery so that that we can make discoveries, and who knows, we might even discover something totally unexpected from it.
Yes, I think that's the beauty of the astronomy. There are so many unknowns and so many unexpected things happen along the way. As long as we build up our detector and waiting there, looking at the sky, there are always surprising things happening.
Yeah, well, thank you very much, Kerr, and thank you everyone for joining us tonight. If you want to see that talk or any of our previous talks again, they're all recorded over on our YouTube channel. Just go to youtube.com/kipac or to our website, kipac.stanford.edu/discover, where you can find all the information about our events. And you can also sign up to our mailing list so we can keep you up to date about what's going on. We'll be back in 2 weeks' time on Tuesday, September 8th, when Dr. Phil Marshall from the SLAC National Accelerator Laboratory will be talking about the Vera Rubin Observatory and how we can use this new telescope that's currently being built, plans to come online in the next couple of years, how we can use that new telescope to explore the universe in whole new ways. So be sure not to miss that. But for now, stay safe, everyone. Great to see you all here. Bye-bye for now.